I'm going to cover the last 2 pages, or really the last page, front and back. I don't have a digital copy of this, so you'll have to follow along in your packet. So I'm on the 7th page, which is titled 5.2 Practice A. And they give us a picture to go along with this, so I'll just sketch that real quick. Okay, so we got a big right triangle here, ABC, and we've got these perpendicular bisectors coming in here. Okay, because E is a circumcenter, so that means these are perpendicular bisectors, so I can mark these as congruent. And now they're asking for information. They're saying that DA is congruent to something. Well, I've marked it as DB, so that's the answer to that one. Number 2, they want to know what BF is the same as. Well, that's FC. EFC, E to F to C, so this right angle is congruent to, and there's lots of answers, any other right angle that's in here. So you could say ABC, EDC, this right angle. You could say EDB, which is a right angle. You could say EFB, which is a right angle. There's lots of choices for that one. Number 4, they're saying that BE is going to be congruent to 2 other segments. Well, E is a circumcenter, and the circumcenter is equidistant from all 3 vertices. So since EB is the distance from E to this vertex, it's going to be the same as the distance from E to A and E to C. So EB actually gets the same markings as these. So your answers are AE and EC. Number 5, they're telling me AD, this is 6, BF is 8, and CE is 10. And they want the perimeter of the whole thing. Well, if that's 6, that's 6. If that's 8, that's 8. If that's 10, this is 10. 20 plus 16 is 20 or 36, plus another 12, 48. Okay, the next picture they give us has a in-center on it. Okay, so G here is my in-center. I get these perpendicular segments. That's measuring the distance from the in-center to each side. So I know that those are going to be congruent. And then I've got the angle bisectors, which is what formed my in-center. Okay, so since these are angle bisectors, I can mark these angles congruent. Let's put our letters on here. A, B, C, there's E, F, this is D. GCA, number 6, wants to know what GCA is congruent to. Well, GCA is this angle. That's congruent to GCD, this angle. Or you could call it GCB if you want. Number 7, ABG. ABG, that's this angle. That's congruent to GBD, this angle. GEC is one of our right angles. It's congruent to any other right angle you want to say. Number 10, what method could be used to prove that GFA, this triangle, is congruent to GEA, this triangle? Well, right now I've already got angle, angle, side marked, so we could use angle, angle, side. I also know that this side would be reflexive to itself, and that would allow me to use the hypotenuse leg theorem. Hypotenuse on both triangles the same as this leg is the same on both, so you could use hypotenuse leg also. Either answer is correct. 11 through 14, we're just doing some true-false. 11 says the angle bisector of a triangle could also be the perpendicular bisector. Well, there's a certain type of triangle where this is true, and that is an isosceles triangle. Because in an isosceles triangle, the perpendicular bisector is also going to bisect the angle. Okay, because this is perpendicular bisector. So these triangles are congruent by side, angle, side, which means their corresponding parts, meaning these angles are also congruent. So that's true. It could be as long as the triangle is isosceles. Number 12. The angle bisectors of a triangle always intersect inside the triangle. Actually, I've got something that'll show us this pretty easily. Give me 1 second, I'll bring it up. Okay, so what I've got here is a triangle, and I've constructed on my Geometry Sketchpad program, which basically does construction geometry for me. I've constructed all of the centers of the triangle. Okay, so I can move my triangle and change it, and the centers move according to what the new triangle looks like. So the question is, the angle bisectors of a triangle always intersect inside. So what I want to look at is the incenter. Where is the incenter as the triangle changes? Is it always inside? Well, let's see if I can get it to go out. Oh, there, it's close. No, it's still in. Right there, it's on, but it's not outside. Okay. Make some weird triangles here. I don't know if I can... Nope. It's never going to, because if you think about it, okay, the incenter comes from the angle bisectors, and an angle bisector is always going to bisect the angle on the inside of the triangle. So since we have all the angle bisectors on the inside of the triangle, they're going to meet inside the triangle. So number 12 is true. They will always intersect inside the triangle. 13, perpendicular bisectors of a triangle always intersect inside the triangle. So let's look at this again. Here, circumcenter, right now it's outside. Okay, there it's on the triangle, inside. Okay, and the determining factor there is if you have an acute triangle, circumcenter's inside. If you have a right triangle, it's on the triangle. And if you have an obtuse triangle, then it's outside. The same can be said for the orthocenter. If you notice the orthocenter up here, when it moves on the triangle, the circumcenter is also on. When it moves out, so does the orthocenter. Okay, and that has to do with the fact that they're both dealing with perpendicular segments. So, 14. Circumcenter is the center of an inscribed circle of a triangle. That's false. The center of an inscribed circle is the incenter. Okay, the circumcenter is the center of a circumscribed circle. Okay, one that touches all three vertices here. 15. I'm not going to draw a picture for this, but on 15, they tell us that the perpendicular bisectors all meet at G. Well, that makes G the circumcenter. Circumcenter is equidistant from all three vertices. So if I know how far G is from one of the angles, which I do, if you look, GB is 13. So that means that GA and GC are also 13. Let's skip down to 17, so right below that, because that's also dealing with perpendicular bisectors. So on that one, P is your circumcenter, and that should be equidistant from the vertices. So that means that PX is going to be the same length as PY, so that's 9. For 16 and 18, we have an incenter. So 16, our incenter is G. It's equidistant from the sides of the triangle, and the sides, or that distance is measured with a perpendicular segment from G to the side. So GF is 5. That means GE and GD are also 5. 18, PN and PO and PM are all the same length. So since PO is 8, so is PM. Okay, last page. On the back side, this is all dealing with mid-segments. Just remember, mid-segments are going to be parallel to the side they don't touch. They're also going to be half as long. So if I put some mid-segments in here, just kind of eyeballing it. Okay. Whatever length this side is, so if this is X, this would be half of x. If this whole side is y, this would be half of y. If this is z, this is going to be half of z. And these will be parallel. These will be parallel. And of course, these will be parallel. So those are the properties we'll be dealing with. Some questions, just 1 through 5. DE is going to be parallel. Well, DE would be like this for us, so it's going to be parallel to its opposite side, which is AC. FE will be parallel to AB. If AB, the big side of the triangle, is 21, EF is going to be half that much, so that's 10.5. BE is half of one side. Well, DF is also half of that same side, so that means in number 4, BE is the same length as DF. They're both 7. 5, DE is 10.2. That's a mid-segment, and that's half as long as the opposite side, so AC should be 20.4. For number 6, they're telling me what YZ is, and YZ is a mid-segment. So if I double my mid-segment, that's going to equal the length of the opposite side, which they're telling me is 5x minus 14. The other equation I could write would be the mid-segment equals half of the whole thing. But since I'd rather not do fractions if I don't need to, I'm going to use this one. So if I distribute, I get 4x plus 6 equals 5x minus 14. Minus the 4, add the 14, I get x equals 20. So if x is 20, they want to know what yz is. This is the equation for yz. I'm going to plug 20 in, and I get 43. Number 7 is a similar thing. If I double the equation of the mid-segment, instead equal to the equation of the whole side, then I can solve this. So this would be 6x minus 8 equals 9x minus 20. Subtract the 6x, add the 20, divide, I get x is 4. They want to know what MO is. This is my MO equation. Plug 4 and I get 36 minus 20, which is 16. Number 9. They give you a picture, and it's pretty easy to just count to find out where the midpoints are. But what you really want to take away from this is finding the midpoints of the midpoint formula. Okay, so if I want the midpoint of AB, I'm going to take the x from A, add it to the x from B, and divide by 2. I'm going to take the y from A, add it to the y from B, and divide by 2. Okay, so this would be 4, 5. Okay, so you can do it with the math and then do the counting to check your answer. So the midpoint of AB is 4, 5, the midpoint of BC is 6, 3, and the midpoint of AC is 2, 2. 10, what they want you to do is use the slope and the distance formula to verify that the mid-segment theorem holds true. Well, the mid-segment theorem says that we should have the same slope for mid-segments and their opposite sides. We should also be half as long. So I'm going to need to find the slope of DF, the slope of DF. So the slope between D, which is at 4, 5, and F, which is at 2, 2. I'm going to take 5 minus 2, which is 3, and 4 minus 2, which is 2, and I get a slope of 3/2. That should be the same slope I get when I do the slope of BC. Well, B is at 8, 6, and C is at 4, 0. So if I take 6 minus 0, I get 6. 8 minus 4 is 4. This reduces to 3/2. So they have the same slope. I also need to check the length. So I'm going to find the length of DF with my distance formula. So 5 minus 2 is 3. 3 squared is 9. 4 minus 2 is 2. 2 squared is 4. Add those together and square root them. I'll get the square root of 13. Do the distance formula here, and I should get twice as much. I should get 2 square roots of 13. So 6 minus 0 is 6. Squared is 36. 8 minus 4 is 4. 4 squared is 16. Add these together in square root. I'm going to get 52. If I break this down, actually I'll do it down here. 52 is 2 times 26. 26 is 2 times 13. I get 2 square root of 13, which is exactly twice as much as that. Number 11. You could draw a picture for this one, but I'm going to show you kind of the easier way. If you're thinking about what mid-segments do, it's pretty easy to count out where the endpoints of a triangle should be based on the midpoints. So these are my midpoints. Okay, this is a midpoint, and it should be parallel to, well, the line that goes through this midpoint. So let's just say I've got, all right, if these are midpoints, okay, and they're making a triangle. If I want to find the triangle that has these as midpoints, the line that goes through this midpoint should be parallel to this line. Okay, so I need to find the slope of this line and use that to move from here the same amount in 2 directions to get endpoints of my big overall triangle. For example, in order to get from here to here, I'm going up 3, up 1. So that's kind of like our slope. Okay, if I go from this opposite midpoint, so I know that to get from here to here, I'm going over 3, up 1. So if I go over 3, up 1, I'll get here. If I go back 3, down 1, I'll get this other endpoint. So up 3, up 1. So from here, if I go up 3, I'm at 8. If I go up 1, I'm at 3. If I do the opposite, I'm going to go down 3 and down 1. That gives me 2 endpoints in my triangle. I just need one more. So from here to here, I'm going down 2, down 2. If I go down 2, down 2, I've got this one again. If I go up 2, I get 6, 5. These are the points of the triangle. And you can check this by finding these midpoints. If I find the midpoint between these, 6 plus 2 is 8, divided by 2 is 4. 5 plus 1 is 6, divided by 2 is 3. So you can check your answers by going in the reverse and finding midpoints based on these. So for 12, okay, we'll do it again. Okay, and again, if this doesn't make sense, you would just want to graph these out and actually count. So I'll show you how to do that. Okay, so I'm going to plot these points 1, 2, 3, 4, 5, 6, 7, 1, 9, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 1, 2, 3, 4. Okay, so the slope of this line is going to be the same as the slope of this. So I'm going to go up 2 over 1, 2, 3, 4. From here, I should go up 2 over 1, 2, 3, 4. I should also go down 2, back 1, 2, 3, 4. Okay, so I get that. So that's 2 endpoints of my overall triangle. If I want to get 2 other ones, okay, to get from here to this midpoint, I'm going over 2, down 3. That means from here, to get the line that's going through this midpoint, that should be parallel to this one, I'm going to do the same movement. Over 2, down 3 brings me here again. Back 2, up 3 puts me here. Okay, and that's going to be the other endpoint of my triangle. So my endpoints are at 7, 9, 3, negative 1, and 11, 3. 13, filling in the blanks. Draw a picture for this one. Let's see, we've got a triangle here, and they're actually telling me it's isosceles, so let's orient it that way. Put in our other segments here. Actually, I guess I should have it oriented the same way they do. I guess it's kind of like this. Something like that. There's a midpoint. I want to connect that to this midpoint. Connect this midpoint to that one. Connect this one to that one. So we've got C, Z, X, B, Y, A. Okay, now in the proof, we're trying to prove that XYZ, so this middle triangle, is the same as XYB, this triangle. So we're trying to get these two triangles congruent. So keep that in mind as you fill in your blanks. Given that A and C are congruent, okay, I know that BC and AB are congruent because that's the base angle's converse. So that's letter A. Since these are midpoints, X, Y, and Z, I know that XY is going to be half of AC, and XZ is going to be half of CB because of the mid-segment theorem. Since BC equals AB, okay, that means that ZY should equal XB. Okay, because XB is half of AB, ZY is also half of AB. Okay, so that's what letter E is. And XZ is going to equal YB. By the reflexive property, XY is congruent to XY. So the triangles are congruent by side, side, side. That's the end of the practice midterm.